This is my thesis proposal. It's a model control from a natural reaction unit and complementing a conditioning unit for gas, the conditioning process. What's the introduction? Mexican hydrocarbon production has been a long pillar of economic and industrial development. However, for the last few years, the production of gas production has clearly decreased. However, what has not decreased is the percentage of gas flaring in Pemex, according to Pemex report. Gas flaring, as we know, is the necessary burn of methane gas of natural gas. And what this does is basically is the burning of gas that cannot be processed, that is not, I would say, hard to process. So therefore, what the companies do is basically they burn this gas and they are not utilizing it. So basically, they produce CO2 out of unnecessary energy process. So they don't convert energy to this type of gas, and therefore my thesis of what I'm trying to implement is to increase the usability of this type of gas so that it will not be said to be burned, be utilized. As what is this type of gas? This type of gas is called associated gas. Associated gas comes from the crude oil reservoirs, as different as normal natural gas that come from the natural gas reservoirs. You can see in the picture that two differences with associated gas and natural gas. And what does this means is that this type of natural gas is more heavier than normal natural gas. This type of gas basically will have a bigger nitrogen, less methane percentage, and at the same time will have a bigger hexane percentage. What does this cause? It is that when through the normal process of natural gas, this type of gas will basically in the uh, in the in the expansion of this type of gas, it will convert into what we call liquid, or basically liquid droplets. We can see this in the picture. This is the gas, basically the gas dew point and bubble point. And in such temperatures, when it decreases, we can see in the normal gas route without conditioning, this type of gas will actually convert to liquid. So uh, it, this is basically the reason why these companies are not producing this type of gas, basically, because they see that this type of gas will become liquid. It will become highly corrosive the was for the gas turbines, and also the what we call the gas pipeline. So this will cause a lot of corrosion. It will basically destroy the gas turbines and also with gas pipelines. And not only that, this type of gas also have a lot of nitrogen percentage. Therefore, also these companies, the conventional energy companies, will not utilize this type of gas because they see as nitrogen as a inert gas. Basically, this nitrogen will make this gas less viable, and this type of gas will not be utilized in what we call the gas pipelines. This gas may be utilized in a gas conditioning unit to gas turbines. However, it will not be transported to gas pipelines. So a lot of this percentage of gas, even though it's utilized, is not completely utilized. A lot of them is, as we call it before, gas flared. So what's the research questions while I'm trying to do? My implementation of a nitrogen directing unit will actually recover more efficiently this associated gas and reduce the gas efficiency in Mexico industry. My plan is to create a dynamic space control model to enhance the operational efficiency and stability of the nitrogen reaction systems. And also we have already designed a dynamic model from gas conditioning unit. I will create a dynamic model for this nitrogen reaction unit in order to utilize it both at the same time and prove that this natural gas can actually be more utilized. Of course, I will consider the thermodynamic and operation considerations. according to the current infrastructure and the current real processing that already exists. So, of course, my solutions and objectives of this is to, as I explained before, design a dynamic model conditioning unit integrated with a nitrogen reaction system to reduce the gas flaring, recovery to associated gas, and transport this gas through Mexico's oil industry. I will ensure a productively and a cost-efficient model. Uh, I will calculate the recoverable of associated gas, of course, using the proper mathematical equations. I will design a dynamic model, of course, utilizing sizing equations to the correct sizing of the equipment. I will validate the model against real world data um, with current literature review. I will conduct, of course, a literature review to check that my equipment, my design is feasible for in according to the physics. And of course, I will evaluate the capital cost of this process, and I will analyze the steady state and dynamic behavior. This will be thoroughly analyzed. I will analyze the results, and I will have my own conclusions of my hypothesis if this will be a robust system, if this will be feasible, and my belief is that this will be so. And of course, I will implement a control strategy in order to make this feasible, since this is a robust system and it requires a proper control in order to be utilized correctly. So the theoretical framework, of course, the gas conditioning unit, it has basically three parts of it. First of all is the equipment sizings. For this conditioning unit has two types of equipments, the heat exchanger and the gas drums. Of course, for the heat exchanger, we use empirical method when we actually obtain the what we call the U value or the U heat coefficient, and this will be obtained using the resistor of the gas of the wall resistance within the heat exchanger. Obtaining this U coefficient, we already obtain the total area of the heat exchanger, and then we can actually design the volume and the of the heat exchanger. Same with the flash drums. Instead, we'll utilize the vapor liquid equilibrium in order to obtain the proper flash drum of the proper sizing of the equipment in order to then utilize it for our then process. Of course, the next step is the steady state modeling. In the steady state modeling, we utilize, of course, the mass energy balance, and also, of course, in the mass energy balance, we have to establish the correct process of all the parameters. Of course, in the heat exchanger, we utilize the heat exchange models because it's the heat exchanger, the mass is, of course, the same. However, the energy is what changes, so we utilize these equations. It's a heat exchanger equation. And of course, in the flash drums, we have, of course, an energy balance and mass and energy balance as well. And we utilize the next equations in order to obtain it. Of course, in a flash drum, we also utilize the vapor and liquid equilibrium equations. And of course, at the end is dynamic model when we prove this process dynamically throughout using, of course, the difference of temperature within time and difference between mass balance within time. And also in the flash drums, the difference is that in the flash drum, we have to actually, for every point of time, we have to calculate the vapor liquid equilibrium. This can be utilized with various processes. Here we're going to utilize a simulation, IC simulation in order to obtain it. However, normally this will be create a differential equation, differential equations according to Penn-Robinson's equation of states. And of course, for the nitrogen reaction unit, we also utilize heat exchangers, but now the difference is that nitrogen reaction unit utilizes something called cryogenic distillation in order to separate the nitrogen from the gas, the natural gas. Therefore, this we utilize a distillation column, and for this distillation column we utilize the Fenwick-Underwood-Gilliland method in order to obtain the equipment sizing, and this method will give us the number of drums that we utilize. However, then we utilize a Rigel stage methods in order to further prove that this the correct sizing of this distillation column. And then, of course, is it comes the steady state modeling, and normally we utilize the mesh equations, the mass equilibrium summation and heat equations. This throughout all the trays of the distillation column. So we can see actually the mass, the balance of the trays. And if we have 40 trays, we actually have to make the state modeling for the 40 trays. So it's actually a very rigorous system. This is the question utilized. And in the end, it comes the dynamic model, of course, similar to the steady state model, but now with a change of in time. And we can see actually mass and energy, and also we have to add the pressure difference in this dynamic model. And the interesting thing will be the building equation, since the vapor liquid equations actually has to be utilized for every point in time and also for every tray. So every tray will have a basically as will behave as a flash drum, and if we have 40 trays, this will have to be done for the 40 trays. So it will be a very rigorous system, but the theoretical framework for this is basically these three equations. And in the end, I propose as a final part of my scope, a state space model in order to properly control, or at least have the model in order to then properly control this system. Of course, before this, we are the different PIDs that we are going to utilize for this process, of course, as is done via this, but this is also part of my scope. I would like to have your opinions to check if this is basically is feasible for this project. And well, a summarized method. This is my methodology. First is the editorial review. Second is the concept design development. Third is the stational model development. Fourth is the dynamic model implementation. Five is the control strategy, and six and seven is of course the analysis and results evaluation. And the eight is will be my document development. So this is my proposal. If you have any questions, I would like to hear them. Thank you.
Thank you so much, Raul. Good presentation. So, just a couple of questions. I don't know if you want to start, David, or okay, I can I can start. Um, so the main we understand that the main point of this research is based on the state space model, right? So once we got the state space model, we can implement a control.
Yes.
So, uh, and also I think the step number 7, economic feasibility, is crucial. So we can start uh, doing some research about this topic. We strongly recommend to if there is some information about how is the economic impact and so on.
Yes. Previously, I have worked establishing various. I already made my whole process one time during my high school, my college degree, and I established a economic model in order to explain why this model is actually better than the previous one. And so I really have a little bit of experience, but I would like to, as you suggest, I will start focusing also my research on this. My current research, it will be focused. It was focused on the natural reaction units. This is a new process that's going to be implemented from the process that we have been working on, and also the state space model have been my main focus on this research. But I will of course add it to my scope this economic feasibility. I believe is very important because part of my thesis will be proving that this process is actually economic feasible in order to be implemented and in order to save what we call the main focus, that is the gas flaring. To reduce the gas flaring, we have to tell the industry basically that this is feasible, basically. So yeah, it's very important for me, I think. Yeah.
Thank you, Roy. We have another question, another two questions. The first one is do you know which is the maximum amount of penalization could be expected?
Well, we can know exactly what's the possible cause of this penalization. In the past, of course, we can going to have corrosion. Actually, the first time the corrosion was taken into account was the first turbine ever created on a for a vapor production. They didn't take corrosion into account, and in one day, in this happened in England, in it was the first plant. One day, the turbine basically corroded completely. It eroded, and in one day they couldn't continue working on them. So that's the first time they discovered corrosion, and corrosion is the cause of what happens if the conditioning unit doesn't work. Basically, it will cause corrosion to these gas or turbines. Uh, to take this into account, we will have to. I could have an estimate. Maybe a completely different study has to be done to know exactly what's going to cost, what's the correction state, how many years of life expectancy this equipment will suffer without conditioning unit. However, we could have a profound research to found other studies that have working onto this that could found maybe in a vapor gas turbine on a gas turbine how does the amount of liquid in those turbines affects the overall life expectancy of it. I think in vapor turbines, this is more common because they use this has to be even more controlled. I expect to find this type of stories is very common. In gas turbines, most of the gas turbines don't use conditioning units, or they don't use what we call associated natural gas. We don't have this type of corrosion when the liquid erodes the turbines. They have more different type of corrosion, or they have more has to be of how the machining is working. However, we know that we have this type of corrosion, but there are not a lot of studies on natural gas associated with associated natural gas. I think those type of studies they do exist, but they are still on working process. That we will find more in the future, of course. But in the case for vapor turbines or other type of turbines, I expect to find this. But it basically has the same impact. Liquid in the gas, liquid in the vapor will erode the turbines. So we can make an estimation even with that.
Thank you so much, Troll. And the second one is you are proposing a methodology to carry out a dynamic simulation.
Yes.
Your methodology could be implemented in a similar process, I mean, in another country?
Yes, of course. This methodology, while we are simulating a exactly process or natural reaction unit, the same methodology of the equipment follows the other processes. For example, we have a distillation column, the way we size that column, the way we provide a steady state, then a dynamic state follows the same principles even in another process. What we could happen, the difference, for example, is that in this process we follow the Penn-Robinson equation of state because those SMX more those are similar or are used in the petroleum industry. And what the Penn-Robinson equation of state does is basically evaluates how the pressure and temperature changes within the process or within the equipment. However, the equations itself do not change. It's just how the analysis of how the fluid dynamics of how the fluid changes within those equipments is the only thing that changes. For example, here I have the example of what is the Penrose-Robinson equation of state follows, and this is equation, and maybe another simulation would use a different equation of state, but they will follow the same equations, even the same equation. For example, this one, they will follow every type of equation. They will follow the same principles. The only thing that must be changed and actually is addressed in this simulation always is what is your state modeling, what is your fluid modeling that you are going to use the fluid properties. And in this case, we follow the Penn-Robinsons because it's for petrochemical uses. Even Penn-Robinson is very used for another uses that has to do with distillation. When always their fluid separation, actually in separation processes, they always use Penn-Robinson. So even in separation processes, even though it's not natural, it's not oil industry, it works with the Penn-Robinson. So they follow the same equations, the equipments. If you have a different type of process, you may change the fluid dynamics associated with that, but they follow the same other equations. So this can be applied to other type of simulation. We can basically change. We only have to change the volume of the equipment, the fluid maybe, and that's it.
Thank you, Raul. So thank you, Carlos. Congratulations for your research work. I guess this will be nice. This will offer a nice results. And as you know, implementing a control strategy for crude oil processes it's profitable. I mean, you can have very good results, as in your previous publication. So thank you for being part of this. I guess we will assist you more in the part of the control engineering, and and that's it.
Thank you. Thank you very much. Just to add, by the fact, of course, I will focus more on the controller strategy from now on. I think I already have a previous knowledge, or I already know what to do for the dynamic models of the either the conditioning unit and also the rejection unit. So my focus right now will be establishing a proper control for this process, and of course, working on this, well, understanding first the state space model for this and then working on it. So this will be my primary focus, and I would like to continue working with you to help me through my development and reach a feasible solution and feasible thesis. Thank you very much, professors.
You're welcome. I will stop the record now.
Okay.